Bridges have long been a symbol of human ingenuity, stretching across vast canyons, turbulent rivers, and open sea to connect people, cities, and continents. But when it comes to the world's largest bridges, the science and engineering behind these colossal structures go far beyond steel and concrete. These mega projects involve cutting-edge materials, complex mathematics, environmental mastery, and often decades of planning. This video explores the core engineering principles, design challenges, and innovative solutions that make the largest bridges in the world possible, backed by data and real-world case studies. The fundamentals: what makes a bridge large? Before diving into the nuts and bolts, it's important to define what we mean by largest. Bridges can be classified by length, height, span, or volume of materials used. For example, the Danyang Kunshan Grand Bridge in China, which holds the record for the longest bridge in the world, stretches over 164.8 kilometers. In contrast, the Akashi Kaikyo Bridge in Japan holds the title for the longest suspension bridge span at 1,991 meters. Meanwhile, the Millau Viaduct in France soars 343 meters high, making it the tallest bridge in the world. Each of these records presents unique engineering hurdles and incredible breakthroughs. Suspension bridges, mastering the art of hanging steel. Suspension bridges like the Akashi Kaikyo and Golden Gate are feats of tension-based engineering. The main secret behind their incredible span lies in the cables, typically made from high-strength steel. These cables bear the entire weight of the deck, which hangs below in a graceful curve known as a catenary. According to a report from the American Society of Civil Engineers, the steel used in modern suspension bridges can handle tensile stresses exceeding 1,770 megapascals, which is over 10 times the strength of structural concrete. Precision is crucial during construction. Engineers use GPS and laser surveying to ensure cable placement within centimeters, despite massive forces at play. Wind tunnel testing also plays a vital role. After the 1940 collapse of the Tacoma Narrows Bridge due to aeroelastic flutter, wind resistance became a top priority. Today, bridges undergo computational fluid dynamics simulations to model airflow and minimize vibration, a technique used in designing the Yavuz Sultan Selim Bridge in Turkey. Cable-stayed bridges, balancing elegance and efficiency. Cable-stayed bridges, like the Russky Bridge in Russia or the Sutong Yangtze River Bridge in China, are similar in appearance to suspension bridges but rely on a different load distribution. Instead of cables draped over towers, the deck is directly supported by straight cables attached to towers, which absorb both vertical and horizontal forces. This makes cable-stayed designs more efficient for medium to long spans, generally up to 1,100 meters. A 2021 study published in the Journal of Bridge Engineering found that the use of high-performance concrete and post-tension steel has significantly enhanced the longevity and load-bearing capacity of these structures. In fact, the design of the Sutong Bridge incorporated HPC with a compressive strength of over 70 megapascals to reduce maintenance costs and increase resistance to corrosion, a major concern in humid or coastal regions. Foundations, building into the unknown. No matter how advanced a bridge looks from above, its strength starts below, in the foundations. Large bridges must contend with unstable soil, shifting tectonics, and deep water. Engineers use techniques such as caisson construction, drilled shafts, and pile driving to anchor bridges securely into bedrock or dense strata. For instance, the Millau Viaduct's piers rest on 15-meter-deep reinforced concrete piles driven into limestone. In contrast, the Jiaozhou Bay Bridge in China used floating platforms to construct massive piers in water over 80 feet deep. Seismic zones present additional challenges. Engineers often isolate bridge piers with flexible rubber bearings or seismic dampers that absorb shock waves, as seen in the Ryan-Antirian Bridge in Greece, built to withstand both earthquakes and tsunamis. Materials, science, stronger, lighter, smarter. The choice of material can make or break a mega bridge. Traditional steel and concrete are still used, but with advanced additives and manufacturing techniques. Ultra-high performance concrete with compressive strengths up to 150 megapascals is increasingly popular. It contains fine aggregates, steel fibers, and specialized admixtures that improve both tensile strength and ductility. Meanwhile, fiber-reinforced polymers are gaining traction for bridge decks and reinforcement. FRPs are immune to corrosion, 70% lighter than steel, and have tensile strengths exceeding 2,500 megapascals. A 2022 meta-analysis by the International Association for Bridge and Structural Engineering highlighted that hybrid designs using both FRPs and traditional materials could extend bridge lifespans by up to 50%. Aerodynamics and climate adaptation. When building over mountains or water, wind becomes a silent but dangerous force. Engineers now use sophisticated wind tunnel testing and CFD simulations to shape bridges that can slice through high-speed gusts. Take the Millau Viaduct again. Its ultra-thin deck was designed to minimize wind resistance, and its shape was adjusted after more than 50 virtual simulations. Climate adaptation is also becoming vital. In Arctic or high-altitude regions, bridges must resist thermal expansion, freeze-thaw cycles, and snow loading. The Confederation Bridge in Canada, for example, was built to endure wind speeds of up to 200 kilometers per hour and ice sheet pressures from moving sea ice. Digital twin technology and smart monitoring. Modern bridges aren't just physical, they're digital too. Engineers now create digital twins, which are virtual replicas of bridges built from real-time sensor data. These twins monitor stress, vibration, temperature, and even corrosion in real time. The Hong Kong-Zhuhai-Macau Bridge, for example, uses over 5,000 sensors to feed data into its digital twin, helping maintenance teams prevent failures before they occur. A study from MIT's Civil and Environmental Engineering Department found that digital twins can reduce annual maintenance costs by up to 30% and predict component failures with over 90% accuracy when combined with AI algorithms. Sustainability, green bridges for a greener future. With the push for sustainable development, bridges are being reimagined for minimal environmental impact. This includes using recycled construction materials, designing wildlife corridors, and limiting the carbon footprint of production. The Ganale Dawa Bridge in Ethiopia was praised for its use of locally sourced materials and minimal disruption to native ecosystems. Even the construction process is changing. Prefabrication, where bridge components are built off-site and assembled later, is being used to cut emissions and traffic disruption. According to the World Economic Forum, modular bridge construction can cut greenhouse gas emissions by up to 40% over traditional methods. The future, self-healing materials and 3D printed spans. Looking ahead, materials science is pushing the limits further. Researchers at Delft University of Technology in the Netherlands have created concrete that uses embedded bacteria to self-heal cracks. Meanwhile, China's Tongji University is experimenting with 3D printed bridge components made from carbon fiber reinforced plastic, a potential game changer for remote or difficult terrains. In 2021, Shanghai unveiled a pedestrian bridge made entirely with robotic 3D printing, a glimpse of what's coming next. As these technologies mature, the next generation of megabridges may not only be taller and longer, but also smarter, cheaper, and greener. Final thoughts. More than just a pathway. The largest bridges in the world are more than just feats of engineering. They're stories of human ambition, technological evolution, and the relentless pursuit of progress. Whether soaring above rivers or weaving through mountains, these structures reflect our ability to shape the world around us. Behind every megabridge is a symphony of science, math, material innovation, and vision. And as our tools and knowledge evolve, one thing is clear. The age of the megabridge is just getting started. If you're fascinated by mega structures, cutting-edge technology, or just love seeing how human ambition takes shape in steel and concrete, this is the place for you. Hit that like button if you learned something new, and subscribe to stay updated with more videos into the world's most incredible infrastructure. Thank you for watching and see you next time.